All right, so now let's start talking about some specific reactions here. The first set of nucleophiles we're going to look at are the oxygen, and actually we'll cover sulfur here too. They live in the same family, so they're pretty similar. All right, so first reaction that we're going to learn about is a hydrate reaction. Ketones and aldehydes in water are always in equilibrium with the hydrate, which notice is just two alcohol groups onto the same carbon. Generally speaking, this equilibrium almost always favors the reactant side, unless you're talking about formaldehyde or maybe acetaldehyde or something like that. But anything larger than acetaldehyde, anything where there's more than one carbon on this one side, are not going to favor the hydrate. This is still a really important reaction because, and you could sort of prove that it's always happening in mixtures of ketones and water, for example, or acetone and water. There's always an equilibrium with the hydrate. Again, even though it favors the reactant side, what's really important about this is you can prove that there's an exchange of oxygen going on. So what do I mean by that? Well, let's just say that I used regular water and a ketone that was labeled isotopically labeled, that had an isotopically labeled oxygen, right? So basically I'm going to be able to monitor where that purple oxygen goes. Well, I would form my hydrate here, where now I have a hydrate where one oxygen has one isotopic labeling, the other one has another isotopic labeling. But then this can be in equilibrium. At this point, the molecule is symmetric, right? So if it's going to go back and form the ketone again, it's a 50-50 toss-up as to which oxygen's actually going to pop off. And so we could have the formation of, for example, just following my isotopic labeling, where now the isotopic label has made its way to the water, right? So basically you can sort of prove using isotopes that this equilibrium is always going on dynamically, even though it does favor the reactant side or favor the ketone or aldehyde. Nonetheless, there's an exchange of oxygen that's going on with the water, right? With the oxygen that's originally bound to water. All right, so then let's look at the mechanism for this. These hydrate reactions can actually occur under either basic or acidic conditions. So let's look at the two here. First, we'll look at under basic conditions, which would be with a hydroxide ion. What's the first step under basic conditions? Remember, basic conditions, we have this really good nucleophile, and so it's going to go and attack that carbonyl carbon. Carbon can't have more than 4 bonds, so that's going to kick that pair of electrons up to the oxygen. So now I have this negatively charged oxygen, and the last step is just going to be to cap that off or protonate it, and I can do that. Water, in this case, will be my acid. It will serve as my acid or my source of proton. Okay, so this is the base catalyzed hydrate formation. Again, notice that I don't have any positively charged intermediates here. All right, now let's go for our acid catalyzed hydrate formation reaction here. Here I'm going to use a weak nucleophile, water, under acidic conditions. What's the first step under acidic conditions? Well, now I have this weaker nucleophile, so I have to create this even better electrophile by protonating that carbonyl oxygen. Now I have a really good electrophile, so my weak nucleophile water can go and attack that electrophilic carbonyl carbon. Still going to make sure carbon never has more than 4 bonds, so that pair of electrons will jump up there. And now I'm left with this sort of intermediate here, where one of my oxygens has a positive charge, and so I have to get rid of one of those protons or deprotonate that group in order to create my second functional group. And again, notice we don't have any negatively charged intermediates under acidic conditions, okay? Only positively charged or neutral. And again, just to hammer this home, 2 different mechanisms that form the same product, right? Under acidic or basic conditions, I still get this hydrate. Okay, just sort of a rule of thumb when you're drawing reaction mechanisms is to think about the acidic and basic conditions, sort of exactly what I've been hammering home about the charge. The bottom line is that you can't have a strong base existing in an acidic environment, right? So you can never have something like this as an intermediate in your acidic environment. It just will not exist. And likewise, you can say this sort of reverse. A strong acid is never going to exist in a basic, under basic conditions, right? So you would never have something like that in a reaction mechanism under basic conditions. You might under acidic conditions, but not under basic conditions, because that's a really good acid. Okay, so that's kind of the charge rule that we were talking about, sort of simplified. Strong base cannot exist under acidic conditions, so no negative charges. And then a strong acid cannot exist under basic conditions, so no positive charges. Okay. All right, so now again, sticking with these oxygen nucleophiles, we can have a very, very similar sort of thing, reaction that occurs between ketones and alcohols, right? But instead of being a hydrate, it's called an acetyl. And I just want to point out that this is, you know, the exact same reaction that we saw before, but instead of having these R's here, if it was the hydrate reaction, they would have been hydrogens. Right? That's the reactions that we just saw. But now instead of taking place between water and the ketone or aldehyde, now we're talking about an alcohol. Oops. Now we're talking about an alcohol, which creates an acetyl. Okay. Notice that also on this side, I have water as one of my products. That's going to be really important later on. All right, so this reaction mechanism looks incredibly similar to what we saw before, but with sort of like back to back, as if we glued two of the ones that we just saw together. So let's just go through here. Reaction mechanisms are going to be a really important part of this chapter, so make sure that you can follow along and do these yourself. What's our first step under acidic conditions? Oh, and I guess let me just make a note. Acetyl formation always happens under acidic conditions. Okay. So what is our first step under acidic conditions? We have to make that really good electrophile by protonating that carbonyl oxygen. So that's how we get our protonated intermediate here. The next step is our weak nucleophile can now attack this really great electrophile, attacking that electrophilic carbonyl carbon, right? So we have our alcohol or oxygen on our alcohol playing the role of the nucleophile and attacking the electrophilic carbonyl carbon. This creates an intermediate where the oxygen has a positive charge on it. All right, so just to clean this up and take a look at this. We have our intermediate here where our oxygen has a positive charge because it's got 3 bonds. Okay, remember that's okay to have a positively charged intermediate because we're under acidic conditions. Now we have to deprotonate that oxygen using some base. Here it's just sort of left to be generic, generic base here. Usually it's with a B, I don't know, you know, it's gonna form an acid, so that's why it's an A here. Nonetheless, you could just have any generic base. It could be the alcohol, it could be another alcohol molecule, whatever. We're just gonna say generic base doing its job here. This creates our hemiacetal, our halfway point, right? And just, I guess to zoom out and make note here what's what, this oxygen that used to be our carbonyl oxygen is now our alcohol here, or our hydroxide group there. And then we have our newly joined alcohol. So this is a halfway point. It doesn't stop there. It's going to undergo yet another round of protonation, but this time I'm going to be protonating that alcohol oxygen. And remember why we do this is to basically turn it into a really good leaving group. Okay, so what happens at the next step is actually this intramolecular reaction that kicks off that really good leaving group. You have the pair of electrons on the, what was formerly the alcohol oxygen, coming down and kicking off that good leaving group. So now I'm left with something ketone-esque, right? And by that, are, I guess, like almost similar to a second step. Notice the similarities between these two here. Okay, I have what is a really good electrophile that's ready for attack by another weak nucleophile. So again, that carbonyl carbon is my electrophile, gets attacked by that alcohol oxygen, kicks that pair of electrons up because carbon can't have more than 4 bonds. And now in my last step here, I just have to deprotonate, right? So just to make sure we all see, my last step here, I have to get rid of this hydrogen, deprotonate that last group. Again, some generic base coming along and snatching that proton, leaving me with my acetyl. Okay. Real quick, I just want to point out, every single step along the way here is reversible, right? We signify that with these 2 double-headed arrows here. So you can do the exact reverse reaction, just going from this end over here, right? And these are readily reversible reactions. They actually don't favor the formation of the acetyl almost ever. And in fact, the one way that we do that, in the case of formaldehyde, again, that's kind of the weird one because it's so small and such an aldehyde having 2 hydrogens. That actually does favor the acetyl problem. Pretty much every other ketone and aldehyde that you see favors the reactants at equilibrium. It doesn't mean that this reaction isn't going on. It just means that 90% of the time, if you took a freeze frame, you would find that most of your molecules are existing in the ketone or aldehyde form, very little in the acetyl form. One of the ways that, well, before we jump onto that, one of the ways that we can change that we can help to favor the actual acetyl formation is to make sure to take the water out as it's being formed, right? So if we can remove the water, that essentially will trap it in that acetyl form, right? So you can imagine, I mean, there might be a few ways to do this. You could distill off your acetyl product. The easiest way, though, is they make these what are called molecular sieves, or little beads that you can just put in your solution that will absorb water as it's being formed. And so that is a way to trap your acetyl, right? To prevent any of the reverse reaction from occurring. There's another example of these acetyl formations that's very special is to use, instead of using, you know, just a regular old alcohol, you use a diol, and then both ends will be attached to the same carbonyl carbon, forming a cyclic acetyl. The exact same mechanism as we saw before, but now both alcohol groups are on that same molecule. This forms a cyclic acetyl. We'll see why here in a second, but the cyclic acetyls are very important. But again, we can, you know, the really important thing is that we can go either way. We can either go to our cyclic acetyl. So real quick, here's my ketone. Here's my cyclic acetyl. I can trap it in that acetyl formation by removing the water. That's what that minus H2O step is. And then I can promote the reverse reaction by just adding water under acidic conditions, okay? This is gonna be really important because the acetyls, the cyclic acetyl in particular, is used as a protecting group for aldehydes and ketones. This carbon becomes a little bit less electrophilic, and as we're gonna see in a second, more importantly is you can prevent it from being reduced, right? So let's say that we had two, you know, this molecule here that has both a ketone functional group, but then also an ester functional group. And I want to reduce just the ester portion to an alcohol, right? Remember, we know how to reduce esters, and actually I sort of put it in a later slide just to remind everybody. But if we use lithium aluminum hydride, we'd actually have to do this in 2 steps. Water. This would be an effective way to reduce the ester to an alcohol. The problem is that it would also reduce, my ketone to an alcohol, right? Well, I don't want that. So what I'm going to do is I'm going to protect the alcohol or the ketone group using these cyclic acetyls, then do the reduction, then remove my protecting group, okay? So first thing I'm going to do is form that cyclic acetyl using my diol under acidic conditions, making sure to remove the water, right? So that's step 1. And then I can go and hit it with the lithium aluminum hydroxide. And then when I add acid as well as water or some aqueous acidic solution, that will kick that cyclic acetyl protecting group back off, and I'll be left with my ketone again. Okay, so this is we've learned about protecting groups before. This is now another protecting group that we're learning about specifically for acetyls. I'm sorry, specifically for ketones and aldehydes. Like I said, the reverse reaction is easy to do. You add water and acid, and that'll sever those acetyl bonds, and you'll get your ketones back. I'm actually going to make you guys, I'm going to make you guys figure that out on your own. But again, just to give you the punchline, it is the exact reverse direction of the reaction mechanism that we learned about. Right, and I guess just to hammer this home, by that I mean this last step here was the deprotonation of that alcohol group. That means that the first step here is going to be, well, the protonation of this oxygen taking me to this species here. Okay, so you're just going to do everything in the exact reverse direction. Okay, but I want you guys to do that as part of your discussion. Okay, and then we can do very similar things, but instead of using an alcohol or a diol, we use a thiol or a dithiol. Oops. Remember that alcohol, oxygen and sulfur live in the same family on the periodic table, so they behave very similarly. This guy here is special though, the cyclic thioacetyl. The reason why the cyclic thioacetyl is so special is because we can hit it with rainy nickel and convert that to an alkane. So effectively, by using these dithiols, forming your cyclic thioacetate, thioacetyl, and then hitting it with the rainy nickel, you can essentially chop off a ketone group and replace it with 2 hydrogens. So we haven't seen that before. Fully reducing a ketone, not to an alcohol, but all the way to an alkane, getting rid of that oxygen altogether. So using these thioacetyls are a way to do that. All right, so just to summarize here, formation of a hydrate can occur under basic conditions, but it can also occur under acidic conditions. You should know both. And do you have to know the mechanism? That's always an important thing. In this chapter, more often than not, the answer is yes. So under both the basic or acidic conditions, you should know the mechanism. All right, for our acetyl formation, These are under acidic conditions. And again, yes, you should know the mechanism. This particular reaction here, it was just acetyl formation, but it was a cyclic acetyl. The reason why this was kind of special is because it can be used as a protecting group for ketones or aldehydes. Okay. You should know the mechanism for this, but again, it's the exact same as this one here. Okay, and then lastly, we have the thioacetyl formation, but really the trick with the thioacetyls is that then we can hit it with rainy nickel and have this reduction reaction. Remember, this just cleaves that oxygen right off. This one you don't have to know the mechanism for, at least not for the second step. The first step is, again, going to be the same as this here, but the rainy nickel part, the reduction step, the part that we really care about when we're talking about thioacetals, you don't have to know.